Great. So, hi everyone. It's good morning. Thanks for coming. Thanks to the organizing team for having such a neat event. So, different paper, holography of information in disordered space. Same set of people, based on also, yeah, same project. So I have three things that I'd like to put here. First one is we just talked about a Hilbert space, but you need to give me a norm for the Hilbert space, which I will. Then we will discuss what cosmological correlators are and what our proposal for cosmological correlators are. And then we'll show that cosmological correlators in the Hilbert space that we have given has a remarkable property called holography of information. So let's refresh our memories. The key thing that we need to take away from the last talk is that the states in the large volume limit take this asymptotic form, where it's e to the is times z. S is a universal factor, which is common to all states. And Z is a diff invariant functional with a possible anomaly in even dimensions, even spatial dimensions. Here's what a Weyl transformation looks like. G goes to omega squared G, and chi also scales according to its own Weyl weight, and the wave functional remains the same. And diff invariance means that G shifts by a Lie derivative of G, chi shifts by a Lie derivative of chi, which is just a coordinate reparametrization on the slice, and Z still remains the same. So what's the naivest wave functional norm that I can give? I tell you that just take psi square. It's mod square. E to the is just cancels out because S is real, so it's just a phase factor. So just mod square Z and sum over all geometries and all field configurations. This also gives the inner product structure. This is a quick exercise that anyone can do, is that if you know the norm of all states in a vector space, you also know the inner product between the states. And essentially, here's what we're doing. So we're saying that our state, we know that so I'm plotting the mod of the state with respect to the determinant of G, and we know that in the infinity limit, it becomes constant. But it may do something funny in the small volume limit. But we're not concerned because this goes to infinity. So if we actually sum up, then the asymptotic form dominates. So we can actually take the limiting form, and this norm at least makes sense in this way. We need not be concerned about what happens to it in the small volume limit. One might worry about the phase of psi, which is coming from Z itself, but we still need not worry because the anomaly that Z has. So if I were to look at how Z squared changes as I change in the volume in the path integral, since the anomaly is purely imaginary, the first term which comes from Z star is negative, and the second term which comes from Z itself is the positive of the negative thing, so it's 0. So even this phase does not matter. So psi squared is exactly Weyl invariant, that is the asymptotic form. So this path integral makes sense. Similarly, we can give an expression for expectation values of different Weyl invariant functionals. If it's AG, you just take A and insert that inside the path integral. Now you have a problem though. In fact, the problem is given to us by the different Weyl invariance itself, is when you integrate over G, you're integrating over all metrics. But there are different metrics which are connected by just a diffeomorphism, a parametrization. There are also different metrics which are often connected by Weyl transformations, but they correspond to the same state. So it's as if in the space of all metrics, I have these trajectories along which my Z doesn't change at all, yet I'm integrating over them. What this gives is a divergence because I'm integrating over some constant function. The solution to this problem, in fact, it's very familiar to people who do gauge theory, is you do gauge fixing. What it means is you insert delta functions. And what these delta functions do is they allow us to cut through these gauge orbits. So now instead of integrating over all of this space, I'll be integrating over a subdomain, so to speak. I don't want to talk about dimensions because all these degrees of freedom are functional, so it's all infinite dimensional. But yeah, so inserting delta functions solves the first problem. And but this incurs a cost. Is when you insert delta functions like this, you incur something called a Faddeev-Popov determinant. That determinant is here. It's the red terms over here. It's integral over fermionic fields called Coast fields. the precise form of this ghost field is not important for this talk, although we have it in our paper. So the blue thing is our solution, and the red thing is the cost for that solution that we get. And the point of the red terms over here is to keep the overall expression independent of the choice of gauge that we have made. So there's a black line and there's a red line, and these are two different choices of gauge. And it's a standard exercise. One can show that this overall functional is independent of what gauge choice I make, which is the choice of how I choose to cut these gauge orbits. But there are some more transformations, which even after gauge fixing, still keep Z invariant. That's another problem. And these transformations look like this. They're translations, where you just do a differ by a constant vector field, no while, or you rotate, and again, no while, or you dilate you dilate your coordinate, and you do a while parametrization. And there's also some special conformal transformations which preserve both the gauge conditions. In fact, these fields are famous for doing so, and these are called conformal killing vectors of the flat space. The SCT is slightly modified, which is metric dependent, but we'll not bother about it in this talk. In fact, we are almost always going to be close to de Sitter, which is conformally flat. So we'll mostly just worry about the conformal killing vectors of flat space. So the issue that they cause is these actually form a group called SO1, D plus 1, which is of infinite volume, causing the norm to yet again diverge. So how do you fix this? So the solution is, let's go near de Sitter. So Gij looks like delta ij plus kappa hij. You should all correct me that this is not actually the de Sitter slice, because de Sitter slice is a spherical slice, but the spherical slice, once you stereographically project onto a flat plane, actually looks like flat plane. So I can look at its perturbation around delta ij. And the tangent state that Priyadarshi talked about can be given like this: the universal factor times the difference between two functionals times some base state Z0, which we can take it to be the Hartle-Hawking state. Doesn't need to be. And that state in the Ket notation looks like this. It's some excitation on top of some Euclidean vacuum. Okay. Now, so we want to cut these gauge orbits again. How do we do this? So the conformal group takes away one point to another point in a geometrical sense. So you can cut these gauge orbits by fixing 3 points in the integrand function. That again is now these 3 extra delta functions. Delta x1 means that x1 stays at x1, and x2 stays at 1, and x3 stays at infinity. What are x1, x2, x3? x1, x2, x3 can be any of these 3 positions which insert themselves in these functionals. So z square is a functional, delta g is a functional, delta g star is a functional. So all of these functionals they need to be integrals over space. So I can pick any 3 of those positions, and I can fix them. And that solves the problem. But then we just have some extra factors of ghost insertions, which we incur from this process. But now if you undo this point fixing, which is now I have these 3 fixed points, but let's take this expression and integrate over x1 goes to gamma x1 and x2 the same and x3 the same, and integrate over gamma over all of the conformal group, which is SO1, D plus 1, and divide by the volume of SO1, D plus 1, which is an identity operation. Nothing should change. Then voila, you get this particular form. This form was actually proposed by Higuchi 30 years ago. What this form says is that the inner product of 2 non-gravitational states, the norm of the non-gravitational state should look like the naive QFT norm divided by the volume of SO1, D. Of course, this expression is formal because these are de Sitter invariant states, and when you take their norm, this diverges. But this volume is also divergent. So in a formal sense, Higuchi showed that this norm is actually finite, and you can actually find orthonormal states. So this is one more validation of our procedure of this inner product. This was just to strengthen the argument that we are on the correct track regarding the inner product. Yeah. So this is Higuchi's proposal. You just you take 2 seed states. Seed state is just a state which gives you the non-gravitational state after de Sitter averaging. And his proposal was that you just sandwich a a de Sitter isometry operation and average it over. Anyway, the point is that we get his proposal back. I have 2 minutes? Okay. So let's move on to the second part of our talk, is cosmological correlators. So in the literature, they're defined as late time de Sitter slicing correlations. And these things are relevant to our life because, so this needs some explanation. So this square is basically de Sitter space. And the inflationary era looks like approximately de Sitter space. And we are sitting somewhere here, which is at a flat slice, which is stuck on top of de Sitter space. The observations that we can make are from these late de Sitter time slices. And that's why these cosmological correlators, which are again, so these X1, X2, they lie on these slices. So these things are of very high relevance for actual observations. This is where all of this gets connected to actual observational physics. So we will give an expression for cosmological correlators. The issue with these correlators is no gauge field is gauge invariant in gravity. So the fact that I have X1, X2, X3 there actually tells us that that expression is not gauge invariant. However, we can make sense of these operators as gauge fixed of operators of this kind, just a bunch of insertions of geometry perturbation and field insertions. And we define the cosmological correlators now as the expectation value of this insertion, except we don't do the fixing of points that we were doing before. We keep it local in these x's. And we find a remarkable property, which is, it ultimately derives from the fact that the wave functionals consisted of delta g's. I'll just take one more minute, I'm almost. The wave functions consisted of delta g's, which were like CFT correlators. The property is this: you take this cosmological correlator and you translate the point x by some constant vector zeta, it doesn't change. And if you scale that vector, then it just changes in this conformally covariant way. You just incur a factor of lambda to the minus q delta, where delta is the weight of our field and q is just the number of chi insertions that C has. What this gives us is this. Let's say this square is the de Sitter slice, and I know all the endpoint correlators in some small subregion R. Then if somebody asks me, what is this correlation function when I have x1, x2, x3, and x4 anywhere else? What I can do is I can scale x1, x2. I can scale all these points back in a small region around the origin via this scaling covariance. And then I can drag them just by translational invariance inside R. And now I know all of these correlation functions. So given all the endpoint functions in a small subregion R, I know what all the endpoint functions in all of de Sitter space slices. This is highly non-trivial. So this is a property. So, and once you know all the endpoint functions, you know the state. So this is what we call holography of information. That's the result, put in a succinct manner. In other words, R has information about R bar, where R bar is the complement region. And this is not true in usual QFTs, which allow split states. I'll not go into split states, but it's in detail, but it's basically things where you don't have information about the complement region when you're confined to a subregion. And this one warning is this does not, yeah, just half a minute. Yeah, and this does not mean that any local observer can predict what the global state is, because cosmological correlators, as we define them, are secretly non-local operators. This result marks a mathematical distinction between QFT endpoint functions and endpoint functions in a quantum theory of gravity. Similar results have been shown in flat space in this paper with Alok Chandramouli in 2021, and again, Chandramouli, Olga, Victor, Subrat in 2022 in ADS. So we just give a summary. We gave a norm for de Sitter states. We show that in a non-gravitational limit, this converges to Higuchi's group averaging norm. We define cosmological correlators as gauge fixed correlators. And we find that these correlators exhibit a version of holography of information. So there are some future directions. There are collision singularities when one computes these inner products or norms. There are collision singularities because of the nature of the functionals that these delta G's and G's, etc. are. This needs to be better understood because we need to show that this inner product or this norm is finite. And our current setup does not have a local observer. We are local observers in our universe. If you don't put a local observer in this setup, you you're not really commentating about local physics. So it'll be interesting to analyze how the algebraic language that Witten and collaborators have about local observers goes with the approach that we have set up. And that's the end of my talk. I'll take questions now. Thanks.
Thank you, Tunir, for the talk. So let's take one question.
So if you have a conformal field theory and if you know the correlation function in any open neighborhood, you can get it get arbitrary correlation function.
Yes.
By scaling.
Yes.
And here, since you're working at large volume, right, you also have a scaling symmetry.
Yes.
So is that the physics why the local the correlation function in an open interval captures everything?
You're saying, is our theory becoming like a conformal field theory in the large volume?
Yeah, in a large volume, because you have a scaling symmetry, right?
Oh, okay. Yeah. Yeah. Okay.
So can I go in for that question also?
Yeah.
Yes. So Ashok, in the conformal field theory, what you're saying works in the vacuum. Of course, in the vacuum state, it's true because the vacuum state has these symmetries that if you're given the correlator in one region, you can expand it to any other region. But there are other excited states in a CFT where you don't have this scaling symmetry. So the interesting point here is that every state in the Hilbert space has this scaling symmetry. So the Hilbert space is like the space of all vacua of all conformal field theories. So that's why the point is that if you're given the correlator in any state, you can get the correlator everywhere. And therefore, knowledge of the correlator in a small region is sufficient to completely identify the state. That would not be true in a CFT. Because you
in
can
a CFT, if you have excited state, right? I mean, you can still write it as a correlation function, right?
You can write it as a correlation function by writing the excited state itself as an action of something on the vacuum.
Exactly, yeah.
But if I just give you I tell you I'm in some state in a CFT, like I don't tell you which state, and I just tell you here are all correlators in a small open set. Can you tell me which state of the CFT you're in? And the answer is no, because there are many states which have the same correlators inside some region and have different correlators outside that region. Here, the claim is weak. Yeah.
Maybe it's what I'm saying is that in a CFT, if you have, say, correlation function between two arbitrary states, right?
Yes.
In arbitrary Ket and Bra states, you can still write it as a vacuum correlation function.
But by writing the Ket and the Bra states as the action of local operators on the vacuum.
Exactly, yeah.
But here, that's not the information we are given. The information we are given is, I'm just telling you the expectation value of some product of some operators inside some region. And I'm asking you to determine which state of the theory that you are in. So I have not told you what operators the states are created by. I've just given you OO for in some small region. And I'm asking you to determine what the state is. And in a CFT, there's no unique answer to that. There are many possible states. In fact, there are states which can be completely different far away, because there might be other operators sitting inside the state, right? Which the psi state might be the action of some operator outside acting on the vacuum. And you wouldn't see it in this list of correlators I give you. Here, the statement is that all states in the theory, like any state psi, has this scaling symmetry. So if I tell you psi, OOO psi, that correlator has a scaling symmetry. In a CFT, that's not true, right? Unless I write the state psi itself as the action of some operator on the vacuum, and then I have to modify that operator also. So it relates psi, OO psi to some other psi prime, OO psi prime. Do you see? Because I have to change also.
Yeah, I mean, if you have CFT, for example, suppose you have CFT like with a string theory constraints, right? You impose the L0 equal to 0. Then it has a scaling symmetry.
I'm sorry, Subrata, could we please take this outside?
Okay.
Sorry, I'm so sorry.
So let's thank Tunir for his wonderful talk and move on to the next speaker.